the different crystal field between octahedral, tetrahedral, and square planar. So how this crystal field theory arise? Okay, the fact that we see the ligands approaching the metal and the attraction and also the repulsion. So in this chapter, you should be able to draw the 5 different suborbitals of d orbitals. Okay, dxy minus y square, dz square, dyz, sz, and dsy. And also you should be able to distinguish which suborbital occupy the lower energy level and which suborbital occupy higher energy level. So for instance, for octahedral, we have 2 energy level. So those with Z component occupy the higher energy level, and for example here dz square and dsy minus y square, where the ligands approach at the axis position. Okay, here dsy square and dz square, and then in between the ligands. So octahedral we have covered before, and today you learn about the magnetic properties of the octahedral complex. So that is to show you between the splitting energy and then the pairing energy. Okay, so this is simply to identify whether it is paramagnetic or it is diamagnetic. Okay, see the difference here. When we talk about crystal field theory, you should draw something like this. Okay, so remember in VBT, when you draw, when you want to determine the magnetic moment, so you draw like a straight line. For example, you draw all the 5 for example, cobalt 3 plus. Okay, so they are, for example, like low spin. Okay, so this is cobalt 3 low spin. So normally you fill in like this, all in straight line. So this is for VBT. But for crystal field theory, remember, you have to split it into 2 energy level. So you have to draw something like this. Okay, so see the difference when you write the electron configuration or when you draw the electron orbital diagram. Okay, between VBT and CFT. Okay, when you draw this, you can simply identify how many unpaired electrons, and you can work out the magnetic moment or the strength of the magnetic field. Okay, and then this is the formula to calculate the crystal field splitting energy. Okay, and then for tetrahedral field, crystal field is opposite to octahedral. So for octahedral, you have 3 at the bottom and 2 at the top. Okay, for crystal field, it is for tetrahedral, it's just simply the opposite of this. Okay, so that is tetrahedral. So it's also similar concept where the high spin or low spin depending on the splitting energy and the pairing energy. Okay. So this is the formula for tetrahedral. So the formula is different from octahedral. For tetrahedral is 0.6 p. How many electrons in the lower energy or E or T2G orbital? Okay, see the difference between the crystal field of octahedral. Okay, so this is for octahedral, and this is for tetrahedral. And then finally, square planar complexes. So for square planar, they have 4 energy levels. Component with Z at the lower energy, they are stabilized, so they become lower in energy, where component with X and Y, they become higher in energy. Why? Because for square planar complex, there are no, because here you see, this is X and Y. So we have ligand on X and Y axis. That's why they have higher in energy. Repulsion between the electrons in the metal, the electrons in the orbitals of metal and electrons of the ligands. So anything without Z's will be higher in energy. And at Z direction, there is no ligand. So that's why the energy levels become decrease or reduce, because there are no ligands at this position or at this axis. So again, square planar is D8 metal ion with strong ligand, and all platinum complexes. Okay, so this is to summarize the CFT. So initially this is free ion, okay, or in VBT we consider as this. They all degenerate. However, for octahedral they are split into 2. For square planar they split into 4 levels, and for tetrahedral they split into 2, and this is the opposite to octahedral. Okay, so as you can see here, between all these, the highest splitting energy is square planar. Okay, square planar has the highest splitting energy. So in terms of splitting energy, or we call it as CFSE. Okay, so for splitting energy, the smallest is tetrahedral, followed by octahedral. Followed by octahedral, and the largest is square planar. Okay, so this is the splitting energy. Okay, so by using CFT, we can successfully explain the electron configuration in the orbital, and also we can explain the spectrochemical series. So the spectrochemical series is arranged, the ligands are arranged based on the splitting energy, and also the color formation in complex, and the stability of the complex, and also we can use the value. So CFSE is crystal field stabilization energy to determine the stability of the complex. So the larger the stabilization energy, the more stable the complex. However, there are some weaknesses of CFT. So first, this theory fails to explain why the fluoride ion, which is very high ionic property but display less ligand field compared to water and ammonia. Okay, because fluoride, it has higher electronegativity to pulse the electrons, but it shows less ligand field. Okay, so you can see this is the position of the fluorine compared to water and ammonia. And also the theory also failed to explain why the Cn and CO give very high ligand field effect with all metals. Okay, so these are the weaknesses of CFT, which is overcome by the next theory that you're going to learn, which is the molecular orbital theory. Okay. So any question? Any question? So what is the unit of crystal field stabilization energy? Okay, so is energy. So sometimes it depends on the question what they give you in the formula. They can give you, for example, dq, or they can give you kilojoule or kilojoule per mole. So that's we can use very different kind of units to describe the stabilization energy. So there is no fix depending on the question. So they can give you, they can ask you to write the unit maybe in dq, or maybe in kilojoule or kilojoule per mole. So depending on the question. Okay, so to test your understanding, okay, you can try answering this question. Okay, and then next week I will share you the answer for this exercise. Okay, so for less paramagnetic, does it mean a high spin or depend? Okay, so to determine the magnetic properties, always you need to draw the orbital diagram so that you can figure out whether it is high spin or low spin. So in the case of, for example, D5, so let's take a look at D5 example. Or we can take D6. So if the complex is high spin, so that means the splitting energy is small. So normally high spin, because they occupy in all the 5 suborbital, so they will have high spin or paramagnetic because there are lots of unpaired electrons compared to low spin. So in general, high spin complexes, they will show paramagnetic compared to low spin. Okay, what is the difference between d orbital splitting diagram and crystal field orbital energy level diagram? Actually, is the same. It's just that so d orbital splitting diagram is more general. Crystal field orbital energy level diagram is more specific. Because when we talk about d orbital splitting diagram, here you learn about the crystal field. orbital. For example, so this is the crystal field splitting energy level diagram. But later on, you will learn MOT. So they have a slightly different orbital splitting diagram. So depending on the question again, so what I can say is D orbital split diagram and crystal field orbital energy level diagram is the same. But D orbital is more general. D orbital spin diagram, they are more general. It can refer to maybe MOT diagram. But when we talk about crystal field orbital energy level diagram, so we understand that it is the split between the D orbital. Okay. Okay. Any other question? So I hope by now you already understand and clear about the differences between VBT and CFT. Because after this, MOT is more complicated. So if you don't understand VBT and MOT, that will be problematic, or that will be difficult for you to understand MOT. So make sure that you know the differences between VBT and CFT, so that later on when you learn MOT, it will be easy for you to understand. So if I can summarize, okay. So for chapter 7, okay, octahedral crystal field, visible spectrum, and then spectrochemical series, and then ligand field strength. So by now you should be able to identify which ligand is strong ligand, which ligand is middle field ligand, and which ligands are weak ligands. So you should already know the ligand field strength. And then about the middle field ligand, it depends on the metal. It's high oscillation metal, and also depend on the splitting energy and the pairing energy. And also for the formula and unit, okay. For the formula and unit, sometimes the question give you frequency or they give you wavelength, so you should be able to convert all these formula. Okay, sometimes they give you in moles, so you have to divide by the Avogadro number or constant. And then sometimes the energy, they may give you the unit in wave number. Okay, so you should be able to, so wave number is centimeter to the power of -1. Okay, so the one that I highlighted in yellow is very important because you should be able to do the conversion. Because some question they ask you to give the answer in wave number, some other question they ask you to give answer in kilojoule per mole. So you should be able to convert these units. Okay, so I think that's it as a summary for this chapter. So try to do the question at the end of this topic to test your understanding. Make sure that you understand this topic so that it will be easy for you to understand the following chapter, which is the molecular orbital theory. Okay, so thank you very much. Is there any other question? Okay. Yes, I will share the answer for the exercise in e-learning. Okay. Okay. Thank you very much for listening. So I shall see you again next week.